So this part, it, the concave and the convex gets it to rise above the water. The first time you were here, you had a V, and what were the issues there?
So the V was very sharp, same sort of width of wheel, but it went to a sharp point. And what that did is it cut through the top of the desert. So the pan here is outstanding, but it has a very hard crust. Then under that crust is a layer of shale. So it's cutting through to the shale and getting damaged. So this kind of more rounded wheel allows it to, it literally crushes the top of the desert and then it rises up out of it.
Fascinating tech. And who comes up with that idea?
So the idea of the wheel being like a boat hull, that was Ron Ayres, our aerodynamicist, and he found that out by going through the old papers of the Campbells, so Malcolm Campbell, Donald Campbell, and he found a design for one of their boat hulls. And so the original design for this, of how that drag worked, the spray drag off the wheel, that was done off the original Wolf Speed record boats and developed into this wheel.
So the more things change, the more they stay the same?
Yeah, I mean, it's where we kind of say we don't want to reinvent the wheel, but the first thing we had to do is reinvent a wheel, but it turns out it's like a boat.
So you've got your wheel, 90 odd kilograms, and at 1,000 miles an hour, 1,600 kilometers an hour, it's spinning at about 10,000 RPM.
Correct. And 10,000 RPM, that means the force on the wheel at the edge, it's 55,000 G. So a kilo of sugar, that weighs 55 tons. And that's had a huge effect on how we've designed that wheel.
And that force, it grows by how much?
So we've spun them up to full speed in a test rig, and it grew by about 3 millimeters in diameter.
My mind, in some ways, I'm in awe, and I'm absolutely boggled. Let's go talk quickly suspension systems at the moment. Cross between an aircraft and a Formula One, you've got pull rod rear suspension with full flexure in here as well.
Full flexure. So the issue we have is again, the loads, it takes a long time to get your head around the loads. So the drag on this wheel as it is, at full speed is 6 tons of drag.
So 6 tons that way.
And if that wasn't a flexure, it would lock up the joint and you'd end up locking your suspension. That'd be really bad. So even the suspension here, we have a normal conventional rose joint, but we have that with clustered needle rollers around it because the loads on it are so great, even something like a rose joint will lock up. And the last thing you want to do is to lock when you've got the forces on, you have on this. But I mean, 6 tons of drag sounds a lot, but at full speed, this car has over 20 tons of drag.
And that's mechanical and aerodynamic, but not just skin drag?
No, so that 20 tons of drag, that's aerodynamic, pretty much all aerodynamic drag. And it's not skin fiction, so you had lots of people saying we sell this really slippery paint, great for race cars, great for aircraft. For us, it's actually the hole we leave in the air behind us. So the vacuum behind the car after you've broken the sound barrier sucks the car back. So again, a lot of the work we're doing this year is to understand how that is, and for next year as we start going through the sound barrier, is look at how you can minimize that base drag.
Because the aerodynamics, as you approach and transcend the sound barrier, the rules kind of change, don't they?
Correct. So I mean, this whole car, again, this year's testing, we're maybe going to 800 kilometers plus this year. It's all about seeing how the car approaches being transonic. So things like the steering the wheel. So the wheel's steered normally. You know, Andy has a steering wheel, he's got a throttle pedal, a brake pedal. The steering wheel drives the front wheels. But above 400 miles an hour, 600 kilometers an hour, instead of them working like your road cars sticking to the ground and dragging the car, they actually work as aerodynamic devices. So above about 400, 500 miles an hour, they're working like rudders, and they're steering the car through the air.
I mean, it's this, guys, this is mind-boggling. I thought that I had a good imagination, but it's mind-boggling. And what a privilege, and I mean, it must give you a thrill working on something like this that is so outside of the ordinary.
Yeah, I mean, as a job, as an engineer, there isn't a job like this. So I've worked aerospace, a little bit of automotive, but you do a job, and there's always been something a bit similar. Even in the current F1 team, you look across the paddock, you work for Airbus, you look at Boeing, there's always something similar to what you're trying to do. This, there isn't. This is when you solve a problem on this, you're the first person to solve that problem. And that is fantastic.
Groundbreaking. Air brakes. So high speed, let's talk through 1,000 mile an hour, 1,600 kilometer an hour run. reaches the end of the mile and then shuts the motor down. So you've got your 27 or 26 tons drag pulling you back as the first part to slow down. The mission is to bring him back safely to base as well. So you've got to slow this 7-ton machine down. How do you do that?
So correct. So Andy's view is, actually my view, going fast is easy. You want to go fast, you put a bigger rocket in. Slowing down is really difficult. So correct, the car has top speed, 20 tons of aerodynamic drag. As we drop down through 800 miles an hour, so around about 1,400 kilometers an hour, we can open the air brakes. So these air brakes are solid carbon fiber. They've got holes in them. The reason there are holes there is to break up the flow behind them, because right behind them we have the rear wheels. So if you imagine like a flag fluttering, if these had no holes in them, you have huge vortices that would shake the rear suspension off the car.
But also the holes help create tremendous drag as well.
So it's all to do with driving the vortexes behind them. So we can open those actually at full speed. This year they're not active. This year we're driving them open to do some test runs right at the end. This year the primary way of slowing the car down is we have parachutes at the back. So this year we're testing the parachute systems, and we'll do some aerodynamic trials on the air brakes.
Just to give you an idea of how fat this is, the thickness of the whole thing, and it's all very nicely shaped. What's that, about 40 odd millimeters? This is a hefty, strong bit of kit. What is the forces on the rod to bring them out?
So they all take something like between 4 and 6 tons to drive them out.
Figures are blooming huge. And the armoring of the side here, what is this for stone damage and to prevent stone ingress into the end of the car?
So this is very much for aerodynamics. So things like, so all the suspension is shielded. So these are all suspension. These are all for protecting the suspension. Again, the rear delta again is to do with protecting the suspension. This is carbon. All the skin up here, this is all titanium. So the whole upper structure of the car is titanium.
And done with a good old English wheel.
English wheel. Again, we are, so things like the cover there for the winglet, that's 3D printed. That's rolled by a man in Bristol. So it is this transfer of technology, some fantastic machining. These are machined and grown from solid to actually artisan skills, doing things like they used to be done in the 30s.
That's a lovely story that 1930, 100 years later, and in the world's fastest land vehicle, you've got, as you say, a man in a shed with a wheel.
Yeah, so this is a huge blend of technology. So we couldn't do what we're doing today without modern digital technology. So analytics, streaming live off the car, all those things are in this vehicle. But at the end of the day, there's a cable that goes to pull a parachute out. There's a part that's been handmade. So it is a huge mixture of technologies.
Plain Bowden cable?
It's not called Bowden, but it's very similar.
And on the fin, which is on the vehicle for the first time today, in the light grey part, those are names of 36,000 people who've each put a small contribution. That's your crowdfunding.
Yeah, so when we went through the financial issues last year, the previous project, Bloodhound SSC, run by Richard Noble, had a huge amount of success with having support to people that genuinely want to be part of the project. When Ian Warhurst bought the project, he said he would honour that obligation, and so all the names that went on that previous project are still carried on this car.
A lovely story, also a bit of digital printing. Right, let's go around to the front of the car. You've got umbilical cords and plain old battery charger keeping the batteries sorted.
Yep, so we have to keep, so we've got aerospace batteries on the car. So again, we just keep them conditioned on car. So we ran the car up this afternoon. So again, we just want to keep it fresh. It's, again, doing the same things tomorrow. We need to be getting ready to run it. So again, we're getting to that cycle, that drum beat of what we do on a run day, a down day. So we've got people checking data, analysing data off the car, but keeping the system fresh, and then making sure we're doing the final checks on things like the cockpit.
Talking about cockpit, let's come and have a bit of a look in the cockpit. It's a cross between aircraft and racing car, and I suppose in an aircraft thing you'd say you've got it's a glass cockpit.
Correct. I mean, there are some analog instruments in there, but again, they're analog but on a glass cockpit. It's configurable, so Andy can change what he has on the cockpit. We can also have different flexions captions and flags that come to alert him what's going on. There is very few automatic systems on the car. So people go, is it autonomous? Could he do, does he actually need to drive it? Yes, he does. He follows, we paint a line on the desert, he follows that line. And it's surprising how much steering you need to keep a car going this quick in a straight line.
Talking about how much steering, you've got very little angle of each wheel steering. Just talk us through the whole steering from the steering wheel, 3D printed titanium, really cool. Talk us through from steering wheel down the column and to the wheels and the mechanisms.
So steering goes to a very conventional rack and pinion steering system. It's got a electric power assistant that we can use. We didn't use that at Newquay. We may well use it this time. We'll see how it works on the Pan. It then goes down to normal sort of track control arms and steering rods on a wheel. The only difference with this, we have double wishbone suspension. To try and make sure we could get the wheel design correct, so the lower wishbone is actually split, so it creates what's called a virtual steering axis. So it's slightly unusual. With a modern car, anything above 10-15 degrees, that would feel awful. This one, our steering is between 2 and 5 degrees, so for us it's perfect, no problem.
And it's got a turning circle of 200 odd, is that meters or feet?
Oh, it's meters, 250 meter turning circle. It's not a thing to get around the car park.
Not at all. Coming down to the front of the car, and nice to see if we can just zip around this side. Henk, we're going on a marathon. You've got to come and have a look. And the really nice parts is to see on the inside and the carbon fiber bulkheads and those tubes. That's part of your array of sensors and pressure sensors in the car, bringing it back into a box.
Yeah, so we've got 3 of these. They're called ZOC boxes. We gather 191 pressure tappings on the car, and we use a scanning valve system, and we can record all that on the car. So if you look across the car, you'll see these little holes. So each of these goes to a pressure tapping. So every single one of those goes to a pressure tapping that will come to one of those boxes. And again, they're under the car, they're over the car. And for this year, we're looking to check they all work. For next year, when we start approaching the speed of sound, then it's looking at the shock wave progressing around the car.
Where do you expect that shock wave? And if you think of this shock wave vertical, where's that going to live on the car forward and aft?
So the shape of the car, if you go from the nose forward, so there is a shock wave from the nose that kind of goes up to the roof. As we come forward, there's another shock wave that starts off from the canopy. So if you look at the shape of the canopy when it's on the car, it's at a very particular angle. That's to set up a shock that goes just above the intake. And then the third shock is literally a normal shock straight across here. And that slows the...
Mark, you said you had a shock wave off the base of the canopy, and the next one is?
So you have a normal shock across the intake, and those 3 shocks slow the airflow down to about 600 miles an hour, 500-600 by the time it goes in here.
And air goes in there. What is this feeding?
So you've got one on each side. These secondary air intakes, so they take in air for bay cooling, but also if there's any other systems in the car that need cooling down, that's where the airflow goes in. Now the interesting thing about the car is when we start going over 1,000 kilometers an hour, just like your bicycle pump gets hot when you pump it up, the air coming in gets hot. At top speed, the air coming in here will be at 160 degrees Celsius. So we can't actually use that air for cooling electronics boxes and things like that. So we actually run iced water tanks, chilled water tanks either side of Andy, and we have a water main running around the car, and that's what keeps all the electronics cool.
I'm kind of lost for words. My mind is processing a whole lot of things, and thank you very much for taking time out and sharing and being so open and sharing, and it's been absolutely magnificent, Mark, and all the very best of luck. We'll be back in a couple of weeks to see this thing run and run fast.
Thank you, been a pleasure. Look forward to seeing you again.
Awesome. Guys, raceday.tv, that's mind-blowing. I'm speechless for once. Thanks for watching. See you again. Cheers.